Hi, welcome back to educator.com. Today we're going to talk about the intermediate value theorem and polynomial division. Previously we talked about how we need to factor a polynomial to find its roots, but we recently saw the quadratic formula which gave us the root of any quadratic without even having to factor at all. So maybe we don't need factoring, right? Maybe there's formulas that allow us to find the roots for any polynomial. Wouldn't that be great? We'd just be able to plug things in, churn out some arithmetic, and boom, we'd have answers no matter what polynomial we were dealing with. Not really. So while there are root formulas for polynomials of degree 3 and 4, they're so long and complicated, we're not even going to look at them. The formula for finding the roots of a cubic of a degree 3 polynomial is really long, really complex, and it's just something that we don't really want to look at right now. So, and a degree 4 would be even worse. So we're just not going to worry about them. And then, not only that, they just simply don't exist for degree 5 or higher. So if you're looking at a degree 5 or higher, there is no such formula for any degree 5 or higher thing. It was proven in 1824 that no such formula can exist that would be able to do that. Thus, it looks like we're stuck factoring if we want to find the precise roots of a high-degree polynomial. So if we're working with a high-degree polynomial and we need to know its roots for some reason, we've got to figure out a way to factor it. In this lesson, we're going to learn some methods to help factor these complicated polynomials. We'll first learn a theorem to help us guess where roots are located, and then a technique for helping us break apart big polynomials. All right, let's go. In the lesson Roots of Polynomials, we mentioned a theorem that every root implies a factor. So implies a factor, that should say. That is, if f of x is a polynomial, then if we've got f of k equals 0, right, k is a root, then that means we know x minus k is a factor of f of x, right? Because if k equals 0, then that means that x equals k causes a root, so x minus k equals 0, and thus we've got a factor from it, right, from our normal factor breakdown. For example, if we've got g of x equals x cubed minus 3x squared minus 4x plus 12, and we happen to realize, hey, when we plug in a 2, that all turns into a 0, and it does, then we would know that g of x is equal to x minus 2, right, this thing becoming x minus 2, and so it would be x minus 2 times blank x squared plus blank x plus blank. We know there's some way to factor that polynomial where something's going to go in those blanks. So 2 is a root. This theorem tells us x minus 2 must be a factor. It doesn't tell us what will be left, but it does make the polynomial one step easier. We know we can pull out x minus 2, so then we can use some logic, play some games, and figure out what's got to go in those blanks. But notice it doesn't directly tell us what's going to be there. If we're lucky, we can sometimes find a root or two purely by guessing, right? We might be like, well, I don't know where the roots are, but let's try -5. Let's try the square root of 2. Let's try pi, right? We might just try something, and surprisingly, it winds up working. That's great. But, you know, is this always going to wind up being the case, right? If we manage to pick something where we figure out the root, and then we figure out that it does get us, we figure out something that gets us a root. We plug in a number and we get 0, then we know we've got a root. And if we've got a root, that means we've got a factor. Knowing a factor makes it that much easier to factor the whole polynomial. But it's hard to guess correctly every time, right? Guessing is guessing. You can't guess every single time. Luckily, there's a theorem that will give us a better idea of where the roots are located. The intermediate value theorem will help us find roots. So it goes like this. If, first, f of x is a polynomial, so for example, we've got this nice red curve here, that's our f of x. Then a and b are real numbers such that a is less than b. So what that means that a and b, just that a and b are, you know, going from left to right. A is on the left side, and then we make it up to b. That's what this a is less than b, just that we know in order that we're going in. And then u is a real number such that f of a is less than u is less than f of b. So we look to figure out that part. We see at a, we are at some height f of a. And at b, we are at some height f of b, right? That's how we get that graph in the first place. Then u is just something between those two heights. So u is just some height level where we put an imaginary horizontal line that winds up saying here is an intermediate value between f of a and f of b, some intermediate height between those two. So the intermediate value theorem tells us that there exists some c contained in ab such that f of c equals u. So we are guaranteed the existence of some c that's going to wind up giving us this height u, right? So basically, if we've got some height u, and that height u crosses between two different heights that go, we have 2 points going from left to right. So we're going from left to right, and we cross over some height during that thing. We start lower and then we end above. We're guaranteed that we had to actually cross it, right? We had to go across it. And since we had to go across it, there must be some c where we do that crossing, where we actually wind up landing on that height. There's something that will give us that intermediate value. Why does this have to be true? Because polynomials are continuous. There's no breaks in their graphs. The only way f could possibly manage to not wind up being on this height u, the only way f could dodge the height u is by jumping this intermediate height, right? The only way that we've got this, the graph is going, 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 and then all of a sudden it would have to jump over that height to be able to manage to not wind up touching it. If our graph touches the height at any point, then we've got whatever point is directly below where it touched that height, that's the location that intersects that intermediate value. That is the thing that's going to fulfill our intermediate value theorem. So on any polynomial or any continuous function, in fact, the intermediate value theorem is true for any continuous function, but we're just focusing on polynomials, they can't jump. Polynomials, continuous functions, they're not allowed to jump. There's no breaks in their graphs. So since there's no breaks, they have to wind up crossing over this height. Since they cross over this height, there's some place on the graph, we just look directly below that, and that guarantees us our c, where f of c is going to be equal to u. There we go. This means we can use the intermediate value theorem to help us find roots. If we know that f of a and f of b are opposite signs, so for example, if we know that at a, f of a is positive, right? We've got a positive for f of a, and then at b, we know that we are negative, we've got a negative for f of b, then we know that there has to be a root. Why? Well, we've got to have some f that's going to make it from here somehow to here, right? It's got to manage to get both of those things. So the only way it can do it is by crossing over at some location, right? It might cross over multiple times, but it has to cross over somewhere. Otherwise, it's not going to be able to make it to that point that we know is below y equals 0. So since f must cross over y equals 0, we are guaranteed the existence of the c at some point where it winds up crossing over. Now, this does not mean that there is only one root. Like we just saw on that second thing I drew, it could cross over multiple times. This theorem guarantees the existence of at least one root, but there could be multiple roots if it bounces back and forth over that y equals 0 on the way to making it to the second point. Okay, so say we find a root of a polynomial by a combination of luck and the intermediate value theorem, right? We somehow manage to figure them out, or the problem just tells us a root directly from the beginning. In either case, with a root, we now know a factor, right? A root tells us a factor. But how can we actually break up the polynomial if we know a factor? How do we divide a polynomial by a factor? For example, say we know x equals 3 is a root of this polynomial. Then we know that there's some way to divide out x minus 3 so that we have x minus 3 pulled out and some blank x cubed plus blank x squared plus blank x plus blank. There's some other polynomial that's going to go with it that the two will multiply, otherwise it wouldn't have divided out cleanly. It couldn't be a factor unless there's going to be this other polynomial where it does divide out cleanly. So how do we actually find out that thing that happens after we divide out this polynomial? How do we do polynomial division? To explore this idea, let's refresh ourselves on good old long division from when we were young. So long ago in grade school and primary school, we were used to doing problems like 1,456 divides by 3. So let's break out long division. We got 1,456. So the first thing we do is 3. How many times does 3 go into 1? 3 goes into 1 0 times, right? So it's 0 times 3. Gets us 0 down here, we subtract by 0, nothing interesting happens yet, 1, and then we bring down the 4. So we've got 14 now. So how many times does 3 go into 14? It goes in 4 times. 3 times 4 gets us 12. We subtract by 12, right? Minus 12. So minus 12, we get 2. Then we bring down the next guy in the running. Let's keep the colors consistent. So we've got 5 coming down, so we now have 25. How many times does 3 go into 25? It goes in 8 times, 16, 24. So now we subtract by 24. So 25 minus 24 gets us 1. We bring down the 6. We have 16. How many times does 3 go into 16? Goes in 5. We get 15. So minus 15. We get 1. Now, we don't have any more numbers to go here, right? There's nothing else. So that means we are left with a remainder of 1. So we've got whatever our very last thing was once we ran out of stuff becomes our remainder. 485 with a remainder of 1. So if we wanted to express this, we could say 1,456 divided by 3. Another way of thinking of that is 1,456 is equal to 3 times 485 plus 1. Or alternately, if we wanted to, we could say 1,456 over 3 is equal to 485 plus the remainder also divided. Because we know that we get the 485 cleanly, but the 1 is a remainder, so it doesn't come out cleanly, so it comes out as 1/3. You could also see the connection between these two things is we simply divide both sides by 3, and that's how we're getting from one place to the other place. So that's what we're getting by going through long division. Really quickly, let's also look at this. 1,456 equals 3 times 485 plus 1. We call this guy right here is the dividend. The thing being divided is the dividend. This guy here is the thing doing the dividing. We call the thing doing the dividing the divisor. Then what we get out of it is our quotient. What comes out of division is the quotient. And finally, what we've got left at the very end is the remainder. Right? These are some special terms. You might not remember those from grade school, but these are the terms that we use to talk about it. Why does that matter? Because we're now going to want to be able to express it in a more abstract, interesting way where we're talking not just about real numbers, but being able to talk about polynomials. So we found that 1,456 divided by 3 became 3 times 485 plus 1. Clearly, we can do this method for any two numbers, and it turns out we can do a very similar idea for polynomials. We call this the division algorithm, this idea of being able to do this. And it says that if f of x and d of x are both polynomials, and the degree of f is greater than or equal to d, that is to say f is a bigger polynomial than d, and d of x is not equal to 0. Why does d of x not equal 0? Because we're not allowed to divide by 0. So if d of x is just simply 0 all the time forever, then we can't divide by it because we're not allowed to divide by 0. So given these things, f of x, d of x, both polynomials. F of x is a bigger polynomial, that is to say higher degree than d, and d of x is not simply 0 everywhere. Then there exist polynomials qx and rx such that f of x equals d of x times q of x plus r of x. So how does this parallel? F of x is the thing being divided. So the thing being divided is our dividend once again. The thing doing the dividing is the divisor. What results after we've done that division is the quotient. And finally, what's left at the end is our remainder. Right? So the remainder right here and our quotient right here. So we've got parallels in this idea of 1,456 divides 3. We've got the same thing coming out here. 1,456, actually 1,456 divided by 3 is not equal to 3 times 485. It becomes this idea. So it's not actually equal. 1,456 divided by 3 is 485 plus a third, but it becomes this idea. So the dividend here, the thing that we're breaking up, our dividend in this idea is 1,456. Let's just knock this out so we don't get confused by it. Our divisor, the thing doing the dividing, is 3. What we get in the end, our quotient is 485, and the remainder is that 1. 1 is left out of it. Now we could also have an alternative form where we write this as f of x over d of x equals q of x plus r of x over dx, where we just turn this into dividing we get between these two by dividing by, sorry, not 3, but dividing by d of x, dividing by our polynomial. So basically the same thing is happening over here. So this would not be 3 times 485, it should be 1 over 3, right? So 1,456 divided by 3 is equal to 485 plus 1/3, because that's 1,456 over 3. So we've got a real connection between these two things. The division algorithm is giving us this idea that if we've got some polynomial f of x, we can break it into the divisor times the quotient plus some remainder, which alternatively we can express as the polynomial that we're dividing divided by its divisor is equal to the quotient plus the remainder also divided by the divisor. This is effectively a way of looking at f of x dividing d of x, seeing what's happening here. Now notice r of x is the remainder. So r of x is the remainder. So in the case when r of x equals 0, then that means we have no remainder, which we describe as dx dividing evenly. So when it divides evenly into f of x, then that means dx is simply a factor, right? 5 divides evenly into 15, so that means 5 is a factor of 15. How do we actually use the division algorithm to break apart a polynomial? Let's look at two methods. We'll first look at long division, and then we'll look at synthetic division. So first off, long division. We'll just take a quick run at how we actually use polynomial long division, and it works a lot like long division that we're already used to. So let's see it in action first, and then we'll talk about how it just worked. So we've got x to the fourth minus 5x cubed minus 7x squared plus 29x plus 30 divided by x minus 3. So we're dividing x minus 3. It's dividing that polynomial, x to the fourth minus 5x cubed minus 7x squared plus 29x plus 30. Okay. So the first thing we do is we ask, all right, how many times does x minus 3 go into x to the fourth minus 5x cubed? Well, really, we're just concerned with the front part. So just look at the first term, x. How many times does x go into x to the fourth? Well, x to the fourth divided by x would be x cubed. So the x cubed goes here. Now that part might be a little confusing. Why didn't we wind up having it go at the front? Well, think of it like this. If we have 12 divide into 24, does 2 show up at the front? No, 2 doesn't show up at the front. 2 shows up on the side because 12 is 2 digits long, so we wind up being at the second place digit as well. 2 digits long, so we go at the second place digit. So same thing going over here. X minus 3 is sort of 2 terms long, so we wind up being at the second term as well. All right, so all those ideas, going to knock them out real quick now that we've got them explained. So that's why we're not starting at the very first place, is because we've got to start out at where they line up appropriately. So we check first term to first term, but then we go as far wide as that thing dividing is. So x cubed is what we get out of x to the fourth divided by x. So now we take x cubed and we multiply x minus 3, just as we did in long division. X cubed times x minus 3 becomes x to the fourth minus 3x cubed. Now, we also in long division, we subtracted now. So subtract. So let's put that subtraction over. Minus, minus, 2 minuses become a plus. So we've got minus x to the fourth attacking x to the fourth. So we've got 0 here. And 3x squared plus negative 5x cubed. Sorry, not 3x squared, but 3x cubed. So negative 5x cubed plus 3x cubed becomes negative 2x cubed. And then the next thing we do is we bring down the minus 7x squared. So minus 7x squared. Now we ask ourselves, how many times does x go into negative 2x cubed? Well, that's going to go in negative 2x squared. So we get minus 2x squared times negative x minus 3 becomes negative 2x cubed. Negative 2x squared times negative 3 becomes plus 6x squared. Now we subtract by all this stuff. So we distribute that, that becomes positive, this becomes negative. We now add these things together. So negative 2x cubed plus 2x cubed becomes 0 once again. Negative 7x squared minus 6x squared becomes negative 13x squared. Next thing we do, we bring down the 29x. So plus 29x. How many times does x go into negative 13x squared? So that goes in negative 13x. And negative 13x times x minus 3 gets us negative 13x squared plus 39x. Now it's this whole quantity subtracting, so that whole thing, we distribute that and becomes addition there, subtraction there. So we have negative 13x squared plus 13x squared, that becomes 0 once again. 29x minus 39x becomes negative 10x. Once again, we bring down the 30 So we get plus 30 here. And now how many times does x go into negative 10x? X goes in negative 10 times, so negative 10 times x minus 3, negative 10x plus 30. We subtract this whole thing, we distribute that, and we get 0 and 0. So we wind up having a remainder of 0, which is to say it goes in evenly. So if that's the case, we now have x cubed minus 2x squared minus 13x minus 10 is what's left over after we divide out x minus 3. So we know our original x to the fourth minus 5x cubed minus 7x squared plus 29x plus 30 factors as, let's write this in blue just so we don't get it confused, x minus 3 times x cubed minus 2x squared minus 13x minus 10. That's what we've gotten out of it. Cool. To help us understand how that worked, let's look at the steps one at a time. You begin by dividing the first term of the dividend by the first term of the divisor. So our dividend is this thing right here. Its first term is x to the fourth. The first term of our divisor, the thing doing the dividing, is x. So how many times does x go into x to the fourth? Well, x to the fourth divided by x. Well, if we're confused by the exponents, we've got x times x times x times x over x. So one pair of them knock each other out. So we've got x cubed now, x times x times x. Great, so that's why the x cubed goes here. It's our very first thing that happens. Next thing, we take x cubed and we multiply it onto x minus 3. So x cubed times quantity x minus 3 becomes x to the fourth minus 3x cubed. Then, so you multiply the entire divisor, this guy right here, by the result, our x cubed, and then we subtract what we just had. So we subtract that from the dividend. So x to the fourth minus 3x cubed, we subtract that from x to the fourth minus 5x cubed. This gets distributed, so we get negative here, plus here, and so that becomes negative 2x cubed. Next thing we do, we bring down the next term. So our next term to deal with is this 7x squared. It gets brought down, and we've got negative 2x cubed minus 7x squared. And then once again, we do the same thing. How many times does x go into negative 2x cubed? It goes in negative 2x squared, negative 2x squared. So then it's negative 2x squared times x minus 3, and we get negative 2x cubed plus 6x squared. We subtract that, and we keep doing this process until we're finally at the end. We might have a remainder if it comes out to be, if it doesn't come out to be 0 for the very last step, or if it comes out to be 0, we're good, we don't have a remainder. All right. There's also a shortcut method that goes a bit faster if the divisor is in the form x minus k. And notice it has to be in the form x minus k. If it's in a different form, like x squared plus something, can't do it. Now notice that you could deal with x plus 3 would just mean that k is equal to negative 3, right? So that's okay. It just has to be x and then a constant. So that's the important thing if we're going to use synthetic division. So it goes like this. We let a, b, c, d, e be the coefficients of the polynomial being divided. So for example, if we have a x to the fourth plus bx cubed plus cx squared plus dx plus e, then we set it up as follows. So k, this k right here, is on the outside of our little bracket thing. And then we set them up a, b, c, d, e. Now the very first step, every vertical arrow, you bring whatever is above down below the line. So A, since there's nothing underneath it, we add terms on vertical arrows so they come down, adding together. So A comes down, there's nothing below it, so it becomes just A. Then you multiply by K on the diagonal arrow. So we've got A, it comes up, we multiply by K, and so we get K times A. Then, once again, we're doing another vertical arrow where we are adding. So we go down, K times A, B plus k times a becomes k times a plus b. Next thing that will happen, we probably want to simplify it just to make it easier, but next thing that will happen, we multiply that whole thing by k once again, and we keep up the process until we get to the very last thing, and the very last thing is our remainder. All the terms preceding that, all the terms in these green circles, is the coefficients of the quotient. So they're going to be the coefficients of the quotient. So if this one, then we'll have a constant here starting from the right, and this will be x's coefficient, this will be x squared's coefficient, this will be x cubed's coefficient, and that makes sense since we started at to the fourth and we were dividing by something of degree 1, we should be left with something of degree 3. All right, let's see it in action now. Once again, dividing the same thing, we've got x to the fourth minus 5x cubed minus 7x squared plus 29x plus 30. So we've got x minus 3. Remember, it's x minus k. So that means our k is equal to 3 because it's already doing the subtraction. So we've got 3, and we set this up. Our first coefficient here is just a 1. So 1 here. What's our next coefficient? Negative 5. Negative 5 here. What's our next coefficient? Negative 7. Negative 7 here. Our next coefficient? 29. What's our next coefficient? 30. And that is our last one because we just hit the constant. All right. So on the vertical parts, we add. So 1 plus blank underneath it becomes 1. Then 3 times 1 becomes 3. Negative 5 plus 3 becomes negative 2. Negative 2 times 3 is negative 6. Negative 6 plus negative 7 becomes negative 13. 3 times negative 13 becomes negative 39. 29 plus negative 39 becomes negative 10. 3 times negative 10 becomes negative 30. 30 plus negative 30 becomes 0. Now remember, this very last one is our remainder, so our remainder is 0, so it went in evenly, which is great, because since we just did this with a polynomial long division and we saw it went in evenly, it better go in evenly here as well. So this is our constant right here, working from the right. This is our x. This is our x squared. This is our x cubed. So we get x cubed minus 2x squared minus 13x minus 10. That's what's remaining. So we could multiply that by x minus 3. And then this whole expression here would be exactly what we started with in here before we did the division. Great. All right, so which of these two methods should we use? At this point, we've seen both polynomial long division and synthetic division. And so which is the better method? Which one should we use when we have to divide polynomials? Now, synthetic division, as you just saw, has the advantage of being fast, right? It goes pretty quickly. But it can only be used when you're dividing by x minus k. Remember, it has to be in this form of linear things dividing only, x and plus a constant or minus a constant. Ultimately, it's just a trick for one very specific kind of problem, where you've got some long polynomial and you're dividing by a linear factor, by something x plus or minus constant. Long division, on the other hand, while slower, is useful for dividing any polynomial. You can use it for dividing any polynomial at all. I think it's easier to remember because it goes just like the long division that we're used to from long, long ago. There's a slight change in the way we're doing it, but it's pretty much the exact same format. You know, how many times does it fit in, multiply how many times it fit in by what you started with, and then subtract that, and just repeat endlessly until you get to the end. And then lastly, it's connected to some deep ideas in mathematics. Now, you probably won't wind up seeing those deep ideas in mathematics until you get to like some pretty heavy college courses, but I think it's really cool how something you're learning at this stage can be connected to some really, really amazing ideas in later parts of mathematics. So personally, I would recommend using long division. I think long division is the clear winner for the better one of these to use. Unless you're doing a lot of the x minus k type divisions, or the problem specifically says do it in synthetic. Like if your teacher or the book says you have to do this problem in synthetic, then you have to do it in synthetic because you're being told to do that. But I think long division is easier to remember, it's more useful in more situations, and it's connected to some really deep ideas that help you actually understand what's going in mathematics as opposed to just being a trick. Honestly, the only reason we're learning synthetic division in this lesson, in this course, is because so many other teachers and books teach it. I personally don't think it's that great. It's a useful trick. It's really useful in the specific case of linear division. If you had to do a lot of division by linear factors, it'd be really great. But, I mean, we're just sort of seeing, oh, we can break up polynomials, so I think the better thing is long division. It's easier to remember. You know, you can actually pull it out on an exam after you haven't done it for 2 months, and you'll remember, oh yeah, it's just like long division, which by now is burned into your memory from learning it so long ago. And so synthetic division, it's really just watered down long division. I'd recommend keep long division in your back pocket. It's interesting, it's not that hard to remember, it's useful in any situation, and it's connected to some deep stuff. And synthetic division is really only useful for this one specific situation, so it's really just a trick. Not a big fan of tricks because it's easy to forget them, easy to screw them up. But long division is connected to deep ideas, and it's already in your memory. You just have to figure out, how do I apply that same idea to a new format? All right, let's see some examples. Let f of x equal 2x cubed plus 4x squared minus 50x minus 100. Use the fact that f of negative 3 equals 32 and f of negative 1 equals negative 48 to help you guess a root. This sounds a lot like the intermediate value theorem. Notice 32 starts off positive, this one's negative, so that means between these two things, right, at negative 3 we're somewhere really positive. At negative 1 we're somewhere really negative. So we know somewhere on the way it manages to cross, so we know we've got a root there. So how are we going to guess it? Well, we might as well try the first thing that's in the middle of them. So let's give a shot for f of -2. Now notice, there is no guarantee that f of -2 is going to be the answer. It could be f of -2.7. It could be f of -1.005. It could be, something that is actually going to require square roots to truly express. But we can get a better sense of where it is. And what the heck, we're students. They probably are going to make it not too hard on us. So let's try -2. Let's guess it. Let's see what happens. We plug in -2. So we have 2 being plugged in. So -2 cubed plus 4 times -2 squared minus 50 times -2 minus 100. OK. F of -2. So that's going to be equal to 2 times what's -2 cubed. -2 times -2, 4 times -2, -8. Keep that negative sign, plus 4 times -2 squared, that'll be 4 times -2 squared is +4, minus 50 times -2, these will cancel out to plus signs, we'll get 50 times 2, just 100, minus 100, so those cancel out, minus 100 plus 100, 2 times -8, -16, plus 4 times 4, 16, hey! They wind up being not too difficult on us, and sure enough, we get equals 0, so we just found a root. F of -2 equals 0, so we've got a root or a 0, however you want to say it, at x equals -2. Great, there's our answer. All right, example 2. So f of x is an even degree polynomial, and there exists some a and b such that f of a and f of b have opposite signs, one positive, other negative. Why is it impossible for f, our polynomial, to have just one root? Okay, so to do this, we need to figure out how we're going to do it. Well, we first think, oh, hey, one positive, other negative. That sounds a lot like the intermediate value theorem that they just introduced to us, so it's likely that we're going to wind up using that. So let's think in terms of that. So f of a and f of b, all right, so we've got two possibilities, right? F of a could be positive, while f of b is negative. Or it could wind up being the case that f of a is the negative one, while f of b is the positive one. They didn't tell us which one, so we have to think about all the cases. Now, how can we see what this is? So we've got an even degree polynomial. Let's start doing this by drawing. So we could have a world where, we've got a positive a, there's some a here, and then some b here where it is negative. And then we could also have, another world where we've got f of a starts off as being negative somewhere, and then f of b is positive somewhere. They don't necessarily have to be on opposite sides of the y-axis, but we're just trying to get an idea of what it's going to look like. We know that we're somewhere on the left, and then we go up to the right. So how's this going to work? And then, oh, well, so we could draw in a polynomial now, right? We could try to draw in a picture, and we might go, okay, so we've got a polynomial come in like this, and we remember, oh, the polynomial could also come from the bottom, so now we have another two possibilities, right? The polynomial is coming from up, or the polynomial is coming from down. So there is poly up, it's coming from above and then going down, or the poly starts below, so poly down, it's coming from the bottom part, it's going up. Maybe that was a little bit confusing as a way to phrase it, but we've got one of two possibilities. Polynomial is coming in from either the top or it's coming in from the bottom. So polynomial at the top, polynomial at the bottom. So those are our two possibilities. Okay. So we could be coming from the top, and let's put in our points as well again. Same points of positive to negative, or we could be coming from the bottom, like this. Then on our negative to positive, we could have negative down here, positive here. Once again, we could be coming from the top, or, oh, whoops, put that on the higher one. We could be coming from the top, or it could be coming from the bottom. Okay, so now let's see, how does it go? Well, we know for sure that the polynomial has to wind up cutting through here, because we're told that it has that value, and then it has to also cut through here. And this one, it cuts through here, and then it has to get somehow to here, so it cuts through here. Hey, and that's basically the idea of the, the theorem, right? We're coming from the bottom, we go up and come down. So we've already hit more than one root, right? We've got two roots minimum here already. What about this one? Well, we go down, and now we have to go up to this one as well. So we go up, and done already. We've got two roots for this one. And this one, we come up, we go through this one, and then we come up, and we go through this one. So these are the two where we still are unsure what has to happen next. Well, remember, what do we know about even degree polynomials? They mention specifically that it's an even degree. Even degree always means that the two ends, if we've got it going down this way, then it means on the right side it goes down here as well. On the other hand, if it goes up on the left side, then it has to go up on the right side. Good old hard to see yellow. We'll cover that in a little bit of black so we can make sure we can see it. So if we're in even degree, they have to be the same direction on both the left and the right side. They could both go down or they could both go up, but it has to, in the end, eventually go off in that way. So who knows what happens for a while here, right? It could do various stuff, but eventually, at some point later on, it has to come back down, which means that it has to wind up crossing the x-axis a second time. So this one has to be true as well. Same basic idea going on over here. Who knows what it's going to do for a while, but because it's an even degree polynomial, we know it eventually has to do the same thing, so it's going to have to come back up, so it's going to cross here and here, so it checks out. So all of our four possible cases, plus, minus, minus, plus, combined with coming from the top or coming from the bottom, the four possible cases, no matter what, by drawing out these pictures, we see, oh, it's impossible, because it's either going to have to hit the two just to make it there, or because it's got the even degree, it's going to have to be forced to come back up and reverse what it's done previously. And we're getting that from the intermediate value theorem. Great. Example 3. Let f of x equal x to the fifth minus 3x to the fourth plus x cubed minus 20x plus 60 and d of x equal x minus 3. Now we want to use synthetic division to find f of x divided by d of x. All right, so first thing to notice, x to the fifth, x to the fourth, x cubed, right? Hey, there's no x squared. So we need to figure out what is x squared. So we can effectively put it in as 0x squared. Remember, the coefficient that must be on the x squared to keep it from appearing, to make it disappear, is a 0. So what we've really got is the secret 0x squared, 60. Because we have to have coefficients for every single thing from the highest degree on down to use synthetic division. So what is our k? Well, it's x minus k for synthetic division. So our k equals 3. So we've got 3 here, and now we just need to place in all of our various coefficients. So our various coefficients, we've got a 1 at the front, we've got a negative 3 in front of x to the fourth, we've got a hidden 1 in front of the x cubed, we've got a 0 on our completely hidden x squared, we've got a negative 20 on our x, and we've got a 60 at our very end for our constant. That's all of them. We've made it all the way out to the constant. So remember, on vertical arrows, when we go down, we add. So it's adding on vertical arrows. So 1 plus blank becomes just 1. And then on these, it is multiply by whatever our k is. So 1 times 3, we get 3. We add negative 3 and 3, we get 0. 0 times 3, we get 0 still. 0 plus 1, 1. 1 times 3, 3. 0 plus 3, 3. 3 times 3, 9. Negative 20 plus 9, negative 11. Negative 11 times 3, negative 33, positive 27. Now remember, the very last spot is always the remainder. So this right here is our remainder of 27. From there on out, negative 11 is our constant. We work from the right to the left. Then our x coefficient, our x squared coefficient, our x cubed coefficient, and our x to the fourth coefficient. And it makes sense that it's going to be 1 degree lower on the thing that eventually comes out of it, the quotient. So we write this thing out now. So we've got x to the fourth plus 0x cubed, so we'll just omit that, plus 1x squared plus 3x minus 11. But we can't forget that remainder of 27. So a remainder of 27 plus 27, but the remainder has to be divided because that's the one part where it didn't divide out evenly. So 27 over x minus 3, because that's what we originally divided by. So this is f of x over d of x. Great. And that is our answer, that thing in parentheses right there. Now, if we wanted to do a check, we could come by and we could multiply by x minus 3, right? If you divide out the number and then you multiply it back in, you should be exactly where you started. So we multiply by x minus 3, so x to the fourth, we'd get x to the fifth, x to the fourth, x to the fifth, minus 3x to the fourth, x squared, so plus x cubed minus 3x squared plus 3x times x plus 3x squared plus 3x times negative 3, so minus 9x, minus 11 times x, so negative 11x, minus 3 times Negative 11 times negative 3 becomes positive 33. And then finally, all of 27 over x minus 3 times quantity x minus 3. As opposed to distributing it to the two pieces, we go, hey, x minus 3, they cancel out, and we're just left with 27. Now we work through and we check out that this all works. So we've got x to the 5th. There's no other x to the 5th, so we've got just x to the 5th comes down. 3x to the 4th. Do we have any other x to the 4ths? Nope, no other x to the 4th, so minus 3x to the 4th. X cubed, do we have any other x cubes? Nope, no other x cubed, so plus x cubed. Minus 3x squared, any other? Yep, they cancel each other out, so 0x squared, minus 9x minus 11x, that becomes minus 20x. Just knock them out so we can see what we're doing. Plus 33 plus 27 plus 60. Great. So we wind up getting what we originally started with. Checks out. So our answer in red is definitely correct. So remember, that remainder, it is the one thing where it didn't come out evenly, so it has to be this divide by. Whatever your remainder is here, divided by the thing you are dividing by, because it's the one thing that didn't come out evenly. All right, final example, find all roots of x to the 4th minus 2x cubed minus 11x squared minus 8x minus 60 by using the fact that x squared plus 4 is one of its factors. So first thing that's going to make this easier for us, if we want to keep breaking this down into factors, right, if we want to find the answers, if we want to find what it is, we've got to factor it so we can get to the roots. So we want to factor this larger thing. So we know that we can pull out x squared plus 4. So if we're going to pull it out, can we use synthetic division? No, because it's not in the form x minus k. We've got this x squared. So we've got to use polynomial long division. So x squared plus 4, we plug in x to the 4th minus 2x cubed minus 11x squared minus 8x minus 60. Great. So x squared plus 4 goes into x to the 4th. Oh, but notice, do we have an x in here, right? So we don't, so it's once again plus 0x. So let's rewrite this. It's not just x squared plus 4. We can see this as a 3-termed thing where 1 is actually sort of disappeared, plus 0x plus 4. Notice that they're the same thing, but it'll help us see what we're doing. So how many times does x squared go into x to the 4th? It goes in x squared, but we don't put it here. We put it here, where it would line up for 3 different terms. 1 term, 2 terms, 3 terms. So it lines up on the 3rd term over here, minus 11x. So it will be x squared here. So x squared times x squared plus 0x plus 4. So we get x to the 4th. This is just blank still, plus 4x squared. Now, we subtract by that. We put our subtraction onto both of our pieces, so now we're adding. So x to the 4th minus x to the 4th becomes 0. Negative 11x squared minus 4x squared becomes negative 15x squared. We bring down our negative 2x cubed, bring down our negative 8x, so we have everything. Negative 2x cubed minus 15x squared minus 8x. So once again, we just ask, how many times does the first term go into the first term here? So negative 2x cubed divided by x squared gets us just negative 2x squared. Oh, whoops, sorry, we're dividing by x squared because negative 2 just x to the 1. So negative 2 times x squared gets us negative 2x cubed. And then negative 2x times 4 becomes negative 8x. We subtract by this, so we distribute our subtraction, so that becomes positive, now we're adding. Negative 2x cubed plus 2x cubed becomes 0, zilch. Negative 8x plus 8x becomes zip, nada. And now we bring down the thing that didn't get touched, the minus 15x squared, the minus 60, and we've got negative 15x squared minus 60, and hopefully it'll line up perfectly. In fact, we know it has to line up perfectly because we were told explicitly it's one of the factors, so there should be no remainder, otherwise something went wrong. X squared plus 0x plus 4, how many times does that fit into negative 15x squared minus 60? Once again, we just look at the first part, negative 15x squared divided by x squared becomes just minus 15. So negative 15x squared, multiplying it out, 4 times negative 15 minus 60. We now subtract by all that. Subtraction distributes, cancels those into plus signs. We add 0 and 0. We have a remainder of 0, which is good. That should just be the case because we were told it was a factor. So we get x squared minus 2x minus 15. So what is our polynomial? It's another way of stating this polynomial. We could also say this as x squared plus 4 times x squared minus 2x minus 15. So let's keep breaking this up. X squared minus 2x minus 15, how can we factor that? X squared plus 4, can we factor that anymore? No, we can't. It's irreducible. If we were to try to set that to 0, we'd have to have x squared. When squared becomes a negative number. There's no real numbers that do that. So that one, that's irreducible. We're not going to get any roots out of that. No real roots for there. X squared minus 2x minus 15. How can we factor this? Just 1's in front of the x squared, so that part's easy. It's going to be x and x. And then what about the next part? Negative 15, we could factor that into, one of them is going to have to be negative. We could factor into 5 and 3. Hey, 5 and 3 have a difference of 2, so let's make negative 5 and plus 3. We check that, x squared plus 3x minus 5x, negative 2x, negative 5 times 3, negative 15. Great. So at this point, we set everything to 0. X squared plus 4, that will provide no answers. So x squared plus 4 equals 0. So nothing there. You know, there's no answers there. X minus 5 equals 0. Turn this one in. That gets us x equals 5. X plus 3 equals 0. This gives us all the roots, x equals negative 3. So our answers, all of the roots for this are x equals negative 3 and 5. And we were able to figure this by being able to break down the much more complicated polynomial into something that was manageable, something we can totally factor, and we had to do that through polynomial long division. All right, cool. Hope you got a good idea of how this all works. Just remember, polynomial long division, that's probably your best bet. Just think of it the same way that you approach just doing normal, good old long division with plain numbers that you did many, many years ago. It's basically the same thing, just in a slightly different format. You know, how many times does it fit in? Multiply, subtract, repeat, 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 get to a remainder. All right, we'll see you at educator.com later. Bye.